Are you Ian Zero? Oh, you're Ian Prime. Okay, so we're all descendants from a mirror universe of you. I'm just going to call you Bizarro Ian. All right, everyone. So thanks for coming. Really excited to be here. So what I'm going to talk about today is kind of interesting. I'm going to give you a little bit about Orchestrate, but we'll get to that after I basically tell you why developers suck. We'll get into that. Who am I? I already got a nice introduction, but I'll introduce myself again. I'm Ian Plosker. I'm the co-founder and CTO of Orchestrate. I know some of you have seen us at our booth. So I'll ask this question. Before today, how many of you had heard of Orchestrate? Or not today, before this conference, how many of you had heard of Orchestrate? 1, 2, 3, 4. Not very many. Well, now that I have this amazing captive audience, all of you will have heard of Orchestrate, and that's great. So what is Orchestrate? Orchestrate is a service that combines the best of NoSQL into a simple HTTP-based service. So our goal is to make storing and querying data so easy that you don't need databases. I mean, we are a database, but you won't be running them. So that's Orchestrate. We'll get back to Orchestrate at the end of the talk. But first, I want to tell you why you suck. Well, not you, but why the software industry has a big problem. And I'm not the first person to identify the problem with the software industry. In fact, the luminaries of the software industry tend to criticize the software industry. So I'm sure many of you have heard of Dijkstra. I imagine that anyone who studied computer science at some point implemented Dijkstra's algorithm, are familiar with the terrible concurrent programming algorithms that we have to deal with, like semaphores that he designed. He was a proponent of structured programming, which you might ask, what is structured programming? Well, anyone who programmed pretty much before 1970 had to deal with this mess of procedural programming. Structured programming is basically what all of our programming languages are today. Everything that's sort of been inspired by C would be considered a structured programming language. Anyway, Dijkstra was just a really interesting thinker beyond being a great computer scientist. And he gave this amazing speech that I imagine, just Google Dijkstra, University of Texas, and I would recommend. He gave a keynote where basically he took the entire computer software industry and just body slammed it to the ground about how the industry had gone crazy by fetishizing complexity. We all know as developers that the simplest algorithm is going to be the best algorithm, but we don't always heed our own advice. So Dijkstra says, simplicity is a great virtue, but it requires hard work to achieve it and education to appreciate it. To make matters worse, complexity sells better. What did he mean by this? Well, the 1970s, which you might think was ages ago, that software has come so far since then, really hasn't that much. But the way that the computer software industry has worked is complexity is how people add value. They start with a really good basic idea, and then they just go and keep complicating it. And this is a natural progression of software. We start with a simple proof of concept, and we move from there. But the question with complexity is complexity does have value, but it depends where you apply that complexity. It depends what domain you apply the complexity to. So you can just go ahead and provide, make a more complicated design, create a more complicated user interface, but you're not necessarily providing value. And even worse, as developers, we fetishize complexity. We like when we build a complex system. We get excited when we build the Rube Goldberg machine system that just works together, that we align the components just right, and somehow it works. And in fact, here's another Dijkstra quote I love. Many a programmer derives a major part of his professional excitement from not quite understanding what he's doing, from the daring risks he takes, from the struggle to find the bugs he should not have introduced in the first place. I think that summarizes myself very well. I get a little bit of a kick out of, trying out that new piece of software I don't understand, and then it just barely works, and, off to production. So, not at Orchestrate, but, with pet projects. So, someone went online. I dug up this SQL query. which is the longest SQL query I could find. This is not generated by an ORM. Some guy got his rocks off over this query, and he posted online and broke down why he loved it. And my point here is just that when we're addressing complexity, I'm just joking around a bit, is that the question we need to be asking ourselves is who owns this complexity we're introducing? So I'm going to read another quote. I have a lot of quotes in this presentation. I don't want to, I like quoting other people rather than just appropriating ideas and pretending they're my own. This is a quote from a great design blog. Unfortunately, I forget who it's from. So, making something simpler is often a case of relocating complexity rather than eliminating it from the user-technology relationship. For example, from a driver's perspective, a manual shift transmission is more complex than an automatic transmission. But from an overall systems perspective, the automatic transmission is equally or even more complex. So, let's just tease it out a little bit. I mean, clearly, the user interface of an automatic transmission is much simpler. I just sort of, move the lever and the car goes. A manual transmission is much more complicated from my perspective, but anyone who actually knows the design of automatic transmissions realizes that they're much more complicated. Now, this is the case across all engineering domains, and we'll tease this out a little bit more later, but I'm just going to throw out some more examples. From your perspective using a credit card is much simpler than cash. I swipe it and I'm done. I don't have to count it. I don't have to think. But the system itself is much more complicated. I think an even better example is Google. Google has a really simple interface, one of the simplest interfaces ever. I mean, Apple gets a lot of credit for making simple, beautiful, well-designed devices, but we don't give Google enough credit for how simple this design is, a text box with a button. I mean, but when you think about it, there's a huge amount of complexity there. The complexity is just not in the user's domain. It's a lot like, the example of the automatic transmission. The same goes for AWS. From my perspective, now obviously this is more complicated than Google, but for me with AWS, I launch up a EC2 instance, and it's a matter of running a simple command line. But from Amazon's perspective, they have this complicated coordination problem of systems and economics and economies of scale that all need to align just so that this command just fires up an instance. I don't even think about it. There's tons of examples that I could just go through. I mean, Twilio, for example, I think someone talked from Twilio yesterday, but Twilio allows you to take advantage of this complex telephony infrastructure while you just have this simple API to work with. Good databases work this way too. Databases are quite complex, but their interfaces can be quite simple. So this is an example of a Lucene query. But on the back end, you might be running Elasticsearch with a really complicated infrastructure. So your ops team is dealing with the complexity where you get to live in this really nice world of simplicity. So we're talking about, we'll get back to this. I want to take a divergence away from talking about complexity and simplicity and the domains that complexity and simplicity can be applied to, and talk about databases, because that's what I love. I love databases. And databases were interesting. I mean, if you trace the evolution of databases, you find that databases evolve in relation to the computer hardware of their time. We're in a weird time, and I have a whole nother talk I could give on why modern databases are not well suited to the modern computing systems, but that's besides the point. Basically, up until 2005, from the advent of the relational database in the mid-'80s until 2005, there were choices, but they were effectively the same. You could have any color as long as it was black. It was, the Model T when it first came out. Of course, you could pick Oracle versus Microsoft or MySQL versus Postgres. But, I mean, effectively, these were all making the same design trade-offs. They're B trees on disk. They have similar query languages. Of course, there's differences on the margins. But it looked nothing like databases in 2013 or 2014, for that matter. Today, there are, at minimum, this is by my count, 25 databases in production that didn't exist 7 years ago. And in fact, I recently had someone do another count, and they came up with the number of 40. And just to, I'm curious, how many people here run a NoSQL database? That's, honestly, it's a lot of people. As I mentioned, I worked for Basho before, and I would give talks maybe 4 years ago, and maybe one person would raise their hand, and they were using Mongo. So pretty impressive. I would guess about a third of the room. How many people are thinking about running a NoSQL database? Handful. Okay. Well, so what we have, the reason why NoSQL came about is because we realized that we needed more than one trade-off. Relational databases were making one particular set of trade-offs, and NoSQL isn't really a consistent category. What NoSQL is really about is it's about providing choice. So I basically here, I'm just going to go over, just so that we're all oriented, sort of a two-dimensional view of how the different database categories align. Obviously, you could add so many more dimensions. This is just two. We're just going to talk about scale up versus scale out. And then on the x-axis, we'll talk about the predominant query pattern. So we're going to start with key value databases. And what do I mean by scale up versus scale out? The idea of scale up is basically as you hit the edges of what your system's doing. With scale-up databases, you add more disk, more memory, faster CPUs. You increase the size of the servers. With scale-out, you add more servers. There might be some controversy over how I categorize these. That's fine if you disagree. But because there's some databases that some people might argue should be in the scale-out, and I didn't put them there. Some people will probably laugh when they realize why some are placed wherever they are. But anyway, key value queries are pretty much the standard for any database. Any good database is built on top of key value, including relational databases, key value stores, excuse me. So, you know, in the scale up, we see things like Berkeley DB, MongoDB, and scale out, we see Riak and Cassandra. We have search is a really important online query type. There we see databases like Solr and Sphinx. In the scale out category, we see Elasticsearch. There's now Solr Cloud, but does anyone here run Solr Cloud? Yeah, I was going to say, but it's a mess. Don't try. Use Elasticsearch. Then there's geoqueries. This is a really growing type of query. I mean, modern applications care as much about who you are or where you are as who you are. So, you know, it's really important to be able to provide geoqueries in a lot of modern applications. You know, see scale up solutions based on Postgres, PostGIS, MongoDB provides it. And Elasticsearch, again, provides relatively nice geo. Actually, in the scale-out area, there's a big gap in the market. And if you could provide some sort of cool distributed archery system, you would, you know, make potentially a lot of money. But open source databases don't make money, so maybe you don't want to do that. So then there's graph databases. How do you construct a social graph? How do you see who your friends' friends are? Who, you know, who are my friends' friends who I'm not friends with? So you can do, you know, recommendation features. This is what graph databases do. In the scale-up world, there's Neo4j, which is a very nice, powerful database, but it's only in memory. It doesn't have any distribution model. Titan has a distribution model, is a nice database. Not quite as powerful as Neo4j, but it's nice because you can have very large data sets. And finally, we have event or time series databases. We have scale-up databases. You can use MySQL, although B trees aren't quite right for time series, but you can do it. We have scale-out databases. HBase works pretty well. There's InfluxDB is a newer one that I don't have here. But the point of all of this is just to show, you know, this is just 2 dimensions. I could add another dimension here just on, you know, how data is persisted. Is it a B tree? Is it a log structured merge tree? Is it SS tables? Is it, you know, is it focused on SSD, hard drive, cloud? Is it, you know, provided as a service? There's all these different dimensions. And this brings us to the database paradox of choice. And this is how we connect it back to complexity. Choice is broad complexity. Is anyone familiar with the idea of the paradox of choice? It's just the idea that with choice, we have a harder time making decisions. And in fact, I find that people tend to make relatively arbitrary database decisions. They either find a database that their friends have recommended to them that might not fit their use case, or the one that the coolest people work for, or whatever sort of arbitrary reason, they often aren't technically evaluating these solutions. And it would be very hard to evaluate every piece of technology you pick on its merits. In fact, social proof is one of the most common ways to pick technology, and there's nothing wrong with that. But we also see when we're implementing modern architectures that because we have these very narrowly focused databases, we have databases that are solving one querying problem, whether it's key value, full text search, geo, event, or graph, that when we want to provide rich applications that know who I am, who I'm friends with, where I am, what I've done, who I've done it with, you need complex data architectures that involve lots of different databases. So you see things like Clout, and for those of you who don't know Clout, it tells you how good you are at posting lolcats on Twitter and how popular your lolcats are. Point being is that Clout's data architecture is composed of 4 separate databases. This is actually a couple years old now. I recently talked to the guys at Clout, and they're running at least 6 databases in production at this point. So this keeps growing. I mean, so once you've found out how to effectively post your lolcats, you need somewhere to host them, and that's where Imager comes in. And Imager, just in a simple architecture, they're hosting images. That's it. They have 6 databases. It may be a little bit complicated for what they're doing, but they've built this infrastructure, and they are quite successful at posting lots of images. I don't know if they're successful at monetizing it, but it's a different story. So all of this brings us to, I want to present you with a way to think about how to design complex systems, how to think about where you should invest in simplicity, where you can build complex things. And so I like to break engineering problems into 3 domains: design, systems, and economics. So design is not so much just how it looks, but it's also how it works, to use a Johnny Ivism. Systems are how it's built, what it's composed of, what the fiddly bits are, and the economics is how you pay for it. People tend to neglect at least one of these domains. In the startup world, it's usually the economic half. In other domains, with most software developers, we tend to neglect the design side. And once we get a nice design, we sometimes neglect the system side. But we really need to think about where we invest our effort, where we produce value for our customers. So let's just break down a couple of products and talk about them in these separate domains. So I'm going to go back to the example I started with, which is Google. So no doubt, Google has a very simple design. It's simple to use, everyone understands it, it's just presented there and you get it. It doesn't, you don't really need instructions on how to use Google. In fact, that's one of the most amazing things about it. But at a systems level, again, there's quite a bit of complexity. It's a huge global system that involves a lot of different amazing technology. And it's fascinating every time Google gives us a little bit of a glimpse behind the covers. But then, we look at this economics domain for Google, and I have to say, one of the things to be suspicious about with Google is from an engineering perspective, they have very, very bad alignment between the design systems and economic model they use, because their economic model is completely disconnected from their product. I mean, their economic model is advertising. Now, kind of aside, but I like to think about how well these 3 domains align for companies. So take the example of Apple. Apple, has really good alignment between designs and economics, right? They sell really elegant devices that you'll pay for. But on the system side, there's not much about having really elegant devices that you'll pay for that leads them to build really great systems to back them. So we see them struggling with cloud constantly because they're not pushed on that domain. Now, if you look at LinkedIn, actually, LinkedIn has high alignment between all 3 domains. While they might not have the simplest design, people who are businessy don't care so much about that. They actually have really interesting systems to do that, and their economic model is selling the information that you posted into LinkedIn. So it's pretty good. Now the scary company, the company that you should be scared of because they have the best alignment, I think, of any company you can find in this sort of evaluation is Amazon. Amazon has, focuses on selling you things really easily, just making it so easy for you to click and buy it. They're really good at building systems. And the reason why they're good at building systems is their economics is all around building economies of scale such that the system of delivery and inventory and getting the product to you after you click that one button is seamless. And this is why, Amazon, while maybe not profitable, has really, really tight alignment and why they're constantly eking out new margins. Whereas Google tends to have to go into completely different product categories to sort of exploit new economics or to build new systems. So it's interesting. Anyway, I'm putting this forward as a way for you to think about engineering. It's been put forward by others, but I like to think about it this way. And I also like to think about where these domains overlap, or how to exploit, complex systems from design, or how to exploit complex economics from systems, or from, design to economics. But really, where we're going to focus, because, where Orchestrate focuses, is on this intersection between design and systems. And I think one of the ways to sort of expose complicated systems, or not one of the ways, the best way to expose complex computing systems with a simple design, or to allow you to focus on design without focusing on systems, is the API. The API allows you to expose utility but hide complexity. You can provide people useful things that do something, but not show all the complicated work that makes those things happen. So, I showed you some examples before: Twilio, SendGrid, Orchestrate. But what this really gives you is leverage. So the idea of leverage from a design perspective is when a complex system has a simple interface. And I like this quote. It's actually from the blog post that I meant to mention before, by Chris Jordan, called "The Complexity of Simplicity," which he says, and I like this nice, clean quote: "Good simplicity is complexity disguised, not complexity denied." So the idea being is that it's how you present that complexity. It's not saying this isn't a complicated thing. It's saying this is a complicated thing, but here's a really easy way to use it. So we'll quickly run through some examples. Twilio, again, shifts the headache of complexity of building a telephony system to a third party, to themselves, and they give you leverage. They, are the fulcrum between your application and this complex telephony system. Same goes for payment processors like PayPal, Stripe, Square, right? You just give them credit card credentials, and you're exploiting this global payment system. SendGrid, similar, and Orchestrate is similar. So, again, Orchestrate could allow you to build a simple, well-designed interface and have this complicated infrastructure behind it. So, looking just at the growth of APIs have been one of sort of the, I think, we talked about this shift to Web 2.0, which was around dynamic applications. I actually think the Web 3.0 shift is a lot around APIs, about exploiting public APIs and public infrastructure such that you can build really great applications with minimal effort. Before, with Web 2.0 applications, you still had to build a lot of infrastructure. Rails was sort of the defining piece of software for me around Web 2.0. The defining piece of software with Web 3.0 is those examples: Twilio, SendGrid, etc. So I always I forget who said it, but I believe it's Peter Thiel who says software is eating the world, but I like adding something to it. If software is eating the world, APIs are eating software, because people are replacing software with APIs. Why run a piece of software if you can put a REST layer on it and sell it as a service? Especially when that software is really complicated to run, when it involves distributed systems with multiple points of presence. So, with all of that, when you're thinking about where your business provides value, whether it's in simplicity, complexity, is it in systems, is it in design, is it in economic modes, you really should kind of think about yourself on the spectrum from simplicity to complexity. And so here I'm more focused on sort of the systems and design rather than the economics, but Apple, for example, really focused on ease of use. Cloud is focused on ease of use, whereas Amazon, on the other hand, is a complicated system, and where their focus is on economies of scale. That's the case for any infrastructure as a service. There are also people who focus on leveraging these things. We also see companies that probably should be focusing on ease of use, probably should have used like RBS or Lloyd's or something like that, but banks should actually be really focused on really simple design, but they're instead very focused on economics because, well, obvious reasons. They care about how big their bonuses are rather than how much satisfaction you get out of using your banking software. Anyway, a William James quote, to throw another quote out there: "The art of being wise, the art of knowing what to overlook." So really, building things, engineering is all about focus. It's knowing where you provide value. So I would argue that for a lot of the web developers in the room, you don't actually provide value in databases. You provide value in building a really great product for your customer, and that's where Orchestrate comes in. Orchestrate allows you to leverage a really great API that's simple, allows you to treat the database problem as a simple problem. All the complexity is somewhere else. Someone else is handling the complexity. I can focus on building a really great, coffee shop locator, or a really great, I don't know, whatever, sort of app you're building, social apps, mobile apps, geolocation apps. So how do we do that? How do we arrive at a simple design that really, again, focuses on giving leverage over a complex system? So really it started with the API. When we went to build Orchestrate, we were like, okay, we want to give our customers leverage. We want to give them power over this database problem. We approach the problem as, we go out there, we see people who are building modern applications. They have a bunch of different query types. They're running a bunch of different databases. It's really hard to run one database well in production, let alone 3 databases. Then you add multiple points of presence, and it becomes an uncontrollable problem where you're throwing, up to 30% of your engineering resources at solving this problem. So how do we solve it? Well, 1, we provide databases as a service. 2, is we provide all of those query types that customers want. And 3, we provide it behind a simple API that takes minutes to get started with. Because one of the lessons we learned when we were building Reoc is that simplicity in interface for most developers sells over correctness in design. And I'm going to make some developers here cry, but MongoDB has a great developer interface, has one of the most incorrect database implementations possible. Like, it's as if you tried to write a bad database. But they won. They won the NoSQL wars, hands down. And the reason is they have an interface that values initial developer productivity, maybe not long-term developer productivity, but still developer productivity over correctness in design. So what we really wanted to do is build something both correct and simple. And that is possible. There's not a trade-off between correctness and simplicity, unless, of course, you don't invest effort in one of those domains. So we tried to make it even simpler than MongoDB, faster to get started, because we were up against, brew, install MongoDB, and then you bring up the Mongo shell and you get going. Well, what's simpler than that? Simpler than that is going to a website and clicking provision. So we provide the API over HTTP. It's JSON in, JSON out. JSON is the standard that everyone's using. I know some people have an affinity for XML, but too bad. I don't. So it's hosted as a service because we wanted to take the complexity of hosting it. The other thing that we learned at Basho, and this was a kind of hard lesson because, again, it kind of gets on this correctness thing. How many people here are familiar with the Cap Theorem? Have you heard of it? Okay, a couple people. So this is a immutable trade-off. Some people will claim they've solved the Cap Theorem. People who understand the Cap Theorem understand that that's ridiculous. Cap Theorem is the CAP theorem. It basically, C stands for consistency, A stands for availability, and P stands for partition tolerance. What consistency means, well, actually, generally the simple version of the Cap Theorem, which is not quite correct, is that you can, in a distributed system, you can only pick two of these properties and you can't get rid of partition tolerance. So you either have to be consistent and partitionable or available and partitionable. What does that mean? So it means that in the face of failures, you have writes coming in to your database, and you have to maintain, state across multiple servers. You need to make a choice. Either I say, I'm in a failure state. I can't guarantee that all of my database servers are going to represent the same state because I can't talk to one of them. And given that choice, you can either say, okay, I'm going to keep consistency and say, no, I'm not going to accept that write. Or you can maintain availability and accept that write, but then have inconsistencies that are eventually patched up. So this is a trade-off often between what's called strong consistency and eventual consistency. Meaning with strong consistency, in the face of failures, you're going to have to say, I can't take any more data. Or you can say, I'm going to take data, but some of your results may be different. I may get, for the same query, different results. Anyway, this is a lot of complexity for developers. The Cap Theorem is really confusing. That was a simple version. There's a long proof of its truth. It's really rooted in the fact, in physics and in the bounding of the speed of light. Besides the point, this is a hard, immutable truth. Developers don't want to face it. We didn't want to present eventual consistency to our users because we found with React it was really complicated to explain to developers why they were getting different results to the same query at different times, and why they had to do things like maintain something called vector clocks so that we could determine causality in a distributed system. We wanted to make it simple, so we actually ended up on the consistent side of things. So, a lot of choices were made. And the choices were all about presenting a simple design, focusing on complexity in the systems, and building a really simple economic model based on selling by usage. So let's dive into the API itself, because I think once you see the API, you'll understand how simple it is compared to other databases out there. So I'm just going to show the sort of HTTP verb and the URL. So to exploit key value, which is really the core data type in Orchestrate, it's simply you get a key from a collection. A collection is akin to a table, for example, a user's table. The key is, let's say a UUID or the username or the email address of the user. And you just get to a collection, put to a collection. You can post if you don't want to provide a key, or you can simply list the contents of a collection. Actually, listing the contents of a collection is a really, really hard problem. Doesn't seem hard, but it is hard from a systems perspective. But again, we were very much focused on solving this design problem of having a simple interface. So if a problem's hard for us, that's our problem domain, is we're providing value in figuring out this complex systems problem and just giving it to you in a simple design. So we solved that problem. If you want to learn how we solved that problem, come by our booth after the talk. And then we're like, okay, well, let's provide search. How do we make search easy? Well, let's not make, who here has used a search database like Solr? I know there were some people, or Elasticsearch. Schemas are one of the hardest things to deal with. And Elasticsearch promotes itself as schemaless, but anyone who uses Elasticsearch realizes that schemalessness is a promise that's not kept. Well, Orchestrate really fulfills that promise. You can just throw data in Orchestrate, and we look at your data, we determine a schema for each document, and we index it. And you don't need to tell us anything ahead about what the structure of your document is. We just construct indexes from the implied schema in each document. What that means is you can perform really nice queries where you can just say, get from a collection, here's a query. Show me everyone whose name begins with Ian, or anyone whose age is from 20 to 35. You can also sort queries very easily. Just provide sort, a field, and a direction. Very soon, you will be able to sort based on geospatial queries. We do support geospatial querying as well using the same feature. Next, you go, okay, well, I can store, let's say, a user profile using key value. I can search for my user profiles. I can discover things based on, look up an interest, whatever. Now I'm building a social network, let's say. I want to describe relationships between the objects. So Orchestrate provides a really simple way to say, apply a relationship between these items. Say that, let's say user A is friends with user B, or user A belongs to group A, and then query those relations. So I can say, for example, get all of this user's friends, or get all of my friends' group memberships. In fact, I should have showed, but you can do multiple steps away. So if you see the second query, get from a collection the key relation of some kind. So like a kind is, can be a friendship, it can be whatever you want. These are arbitrary, but you can do multiple steps. You could see who a user's friends of friends are, for example. Again, really nice and simple. The API is very consistent, and you don't even think about what's going on behind the scenes. It's not relevant to you. And finally, we have a time-ordered API. And what this allows you to do is in each key value item, there's basically a time-ordered sub-collection. So, for example, in a social network, I might have status updates, pictures of the food I've been eating from restaurants that you'll never go to because they're, halfway across the world. This seems to be what most of my friends do on social networks, at least. So I need a way to express those status updates. So that's what this feature is for. So basically, my events are embedded within a key value object. So you can get from a collection and a particular key an event of particular kind. So you might be status updates, what I ate, a photo, whatever it might be. And so we can get events, we can store them, we can store them with a user-provided timestamp, and I've messed up the last example, but you can also do some interesting things with modifying timestamps. But this gets to really some of the interesting advanced features of Orchestrate. So, I talked about how obscuring complexity is really important, and we do that in Orchestrate, but we provide advanced features where they're necessary without crudding up the API. So one thing that we really believed in when we were building Orchestrate, and part of this is from a lot of the work Rich Hickey has done on closure and atomic, is in the power of immutable data. So, typically when you're storing data in the real world, let's say a medical record, when you change something, when you add something to a medical record, you don't erase what was already there. You add, you revise, you don't destroy, whereas in software, we treat everything as mutable and we just write over it. Orchestrate treats everything as immutable. It never changes it. In fact, our key value API essentially treats data as a time series. So when you store data to a key, you're storing a new head revision. Imagine it like Git. And then you still have all of the previous revisions stored in Orchestrate. You can query them, you can get them back. And this means that you're never losing data. It's a really nice property. We also provide optimistic concurrency control so that you can manage distributed applications. And like I was just mentioning, historic queries, which allow you to sort of observe the change in immutable data. So that's Orchestrate's API. Basically, I'd like to, wrap up. What I want you to get away from this talk is one, think about where you provide value to your users. Is it in providing simple design? Is it in providing, power through the complexity of the systems you're exploiting? Is it some, economic model that allows you to provide value to your users? And once you've addressed that problem, how do you best solve it? Again, on every sort of scope you're in, you can look at this, on, design, systems, economics on the scale of your business, but any particular problem sort of reproduces the same set of questions. When we were building Orchestrate, while we might have not explicitly put it in these terms, we were very much focused on, how do we build something that provides a simple economic model, a, usage-based API for data that has a simple interface, but allows users to exploit, the best-in-class database design. So with that, I'll end my talk. If you guys have any questions, be here to answer them. Yep.
Well, hold on 1 minute. Let's do this in the prep order. Let's give you a round of applause.
Okay.